Learn like a pro.
Have you ever really thought about how a battery works? I mean, it's pretty much everyday magic, right? You take two different kinds of metal, you stick them in some kind of liquid, and poof, you get electricity. It sounds way too simple to be true, but the chemistry behind it is actually super cool. So let's break down exactly how that magic happens.
So what is the secret here? How on earth can a couple of metal strips sitting in a solution create an electrical current? Well, it all boils down to a sort of chemical argument, you could say. One of the metals is just way more desperate to get rid of its electrons than the other one is. And that imbalance, well, that's everything.
The answer to our big question lies inside a nifty little device called a simple cell. This is where we see the transformation, where still, quiet chemicals suddenly spring to life as a moving electrical current.
At its heart, a simple cell is just an energy converter. It's designed to take the energy that's just sitting there, stored in chemical bonds, and turn it into the flow of electrons that we call electricity. And you know the best part? The whole reaction happens all by itself. It's totally spontaneous. It wants to happen, and we're just clever enough to harness that energy.
Okay, let's meet the key players. The secret sauce is that you have to use two different metals, and the more different their reactivity, the better. The more reactive metal, the one that's super eager to give away its electrons, becomes what we call the anode. This process of losing electrons is called oxidation. Meanwhile, the less reactive metal becomes the cathode, and its job is to accept those electrons in a process called reduction. This difference in attitude towards electrons is the engine that drives this entire system.
To really get this, let's make it more concrete. Let's follow the story, the journey of a single electron. We're going to use a classic setup, a cell made with magnesium and copper. This is where the real action begins. Our story kicks off at the anode, which in this case is our strip of magnesium. It's way more reactive. Just picture the atoms on the surface of that magnesium strip. They are so generous with their electrons that they willingly just give up two of them and then dive right into the solution as magnesium ions. That right there is oxidation in action.
And here's what that looks like as a chemical reaction. You've got solid magnesium, MgS, turning into a magnesium ion floating in the solution, Mg2+, and releasing two electrons in the process. And because the metal is literally dissolving away, you can actually watch the magnesium strip get smaller and smaller over time. It's physically losing mass.
So what about those two electrons magnesium just released? Well, they don't just hang around. They travel through the wire all the way to the other side, the cathode, our less reactive copper strip. And over there, waiting in the solution, are copper ions. These ions are drawn to that now electron-rich copper strip, where they can happily grab those incoming electrons.
And here's the equation for that side of the story. The copper ions in the solution, Cu2+, take those two electrons and turn back into solid copper atoms, Cus. They literally plate themselves onto the electrode. So the complete opposite happens here. You can see the mass of the copper electrode actually get bigger as new layers of solid copper are built up on its surface.
And that's it. That's the whole show. The journey we just followed, that directed one-way flow of electrons from the magnesium anode through the wire to the copper cathode, that is an electric current. We've just converted chemical energy into electrical energy. Pretty neat, huh? Okay, so we've got a current. Fantastic. But not all of these simple cells are created equal. Some will give you just a tiny trickle of electricity, while others can produce a serious flood. So what actually determines the strength of that current? The voltage.
The voltage is all about the gap in reactivity between the two metals. Think about it like this. Imagine a super crowded room connected to a completely empty one. The more jam-packed that first room is, the greater the force of people rushing out when the doors open. It's the same idea with electrons. As you can see here, the reactivity difference between magnesium and copper is massive, so it produces a really high voltage. But the gap between iron and copper, it's much smaller, creating a weaker push and, you guessed it, a lower voltage.
All right, now that we've got a handle on the simple cell, which, remember, produces energy, let's flip this whole concept on its head to really make sure we understand it. It's time to meet its opposite, the electrolytic cell, which actually consumes energy.
So the very first thing you should notice here is that external battery sitting at the top. See, unlike our simple cell, which is a battery, this electrolytic cell needs a battery to work. It uses that outside source of electricity to force a chemical reaction that would never, ever happen on its own. It's the complete reverse. We're putting electricity in to get a chemical change out. Now, this whole producer versus consumer thing leads to what is probably the most confusing part for a lot of people. The polarity of the terminals, it gets flipped. So why is the anode negative in one cell but positive in the other? Let's clear this up once and for all.
Okay, look at our simple cell. The anode is the source of the electrons, right? They build up there before they flow out. That buildup of negative charge makes the anode the negative terminal. But in an electrolytic cell, the external battery is in charge. It pulls electrons away from the anode by connecting it to its own positive terminal. So while oxidation always happens at the anode, its charge just depends on one simple question. Is it naturally pushing electrons out, or is an outside force yanking them away?
All right, let's do a quick check-in. Time for a little quiz to make sure that really crucial concept has locked into place. Let's test your knowledge of the terminals.
So let's focus just on the simple cell, the energy producer we started with. Which electrode gets that negative sign, and what's the fundamental reason it gets it?
The answer is the anode, and the reason is simple. It's because it's the more reactive metal, the one that is spontaneously losing its electrons. It is the natural starting point, the source of the electron flow, and that makes it the negative pole of our little chemical battery. So, the next time you look at a battery or see a diagram of a cell, just remember that simple distinction we covered today. Is it producing energy, like a simple cell, or is it consuming energy, like an electrolytic cell? One creates a current from chemistry, and the other uses a current to create chemistry. And understanding that one difference is really the key to all of electrochemistry. Thanks for diving in with me on this one.